just sit near. The presenter is a first-year PhD student in the Department of Computer Science Engineering at the Hong Kong University of Science and Technology. He's from Kai Chen's group, and her research interests lie in data center networking, with a particular focus on the host networking. And SmartNIC's first-year students.
Yeah.
Okay, Qijing.
Hi everyone, I'm Li Qijing, and in this talk I will present to you our system named CARC, which is a catch-aware I/O rate control for RDMA. This work is done in the IC lab of HKUST. RDMA has become a cornerstone technology in modern data centers due to its high throughput and extremely low latency. However, recent work has revealed that the congestion arises in the last mile of the I/O path due to the inefficiency in the memory hierarchy. Before we dive into the I/O congestion, let us see a perfect scenario of an RDMA I/O path where no I/O congestion happens. In the receive side, RNIC first receives packets in the receive buffers. Then the RNIC fetches wokes in wookie cache or host memory to get the metadata like the destination memory address. And initiates DMA to the last level cache through DDIO acceleration, which enables DMA to bypass memory. After that, in step 4, application can access data in IIC directly and replenish wookie if needed after processing data. However, when I/O congestion happens, where ILC capacity is not enough, things are different. In the step 3, DMA operation will trigger DDL write allocate, which will allocate ILC space for new data and evict old data to DRAM. In the step 4, if needed data is evicted from ILC, application need read from DRAM, which also bring eviction. As the receive ring space is used sequentially and repeatedly, there is a negative cycle. DDL cache eviction leads to net CPU cache misses. CPU cache misses bring new cache eviction and ILC occupies, which makes the DDL write allocate happen again. This process also makes the memory contention more severe, as there is memory bandwidth waste that evicted data will be used soon. All these things result in bad performance. Existing work like host CC introduce host congestion signal. The I/O buffer occupies to traditional congestion control. Such solution is coarse-grained as it is not aware of the detailed cache occupies. It sends back a CMP once I/O occupies exceed a threshold and lead to same rate reduction, which is 1/2 in DCQCN. In order to solve the I/O congestion problem, we first modeling it. Here is a simplified case of cache replacement in network I/O, where the receiver uses 8 buffers for receive queue, and over cache policy is basically ILU. Assume over cache can accommodate 5 buffers. Among it, the DDL cache, which is marked as the dark, can accommodate 2 buffers, and non-DDL cache can accommodate 3 buffers. According to the DDL rules, when the DMA destination address is not in cache, DDL will allocate space in DDL cache. Otherwise, DDL will put data directly to cache, no matter what the cache type is. Okay, now here is a receive side scenario. In step 1, in-cache memory are DMA'd to pre-post buffer. During this process, some data will be evicted from ILC, and in the end, the data 6 and data 7 will be in the ILC. And in the second step, application began to read the data 0 to 3 from the DRAM, which will also bring the eviction of unused data 6. In the step 3, RNIC DMA 4 new message to newly posted buffer 0 to 3, And there is no eviction happen because the buffer 0 to 3 already in LLC. And in step 4, application reads the last round message from DRAM, the message 4 to 7. As this pattern continues, the cache misses rate will keep at 100%. We model such I/O congestion as a producer-consumer speed mismatch problem and represent the state transfer of cache system with the red figure. V1 here means the network ingress rates, and V2 here means the CPU processing rates. The states represent a different degree of unprocessed data volume, and the state transfer is decided by speed gap and time span. For instance, S1 means the unconsumed data size is less than DDL cache size, where no cache misses happen. S2 represents the unconsumed data size is larger than DDL size, but less than LLC size, in which case, those cache misses happen due to ALIC eviction in the beginning. After all buffers are read from LLC, cache misses stop. The last two states, S3 and S4, represent the unconsumed data size is larger than LLC size, but limited by received queue size. This is the case of the example in last slides. In these two states, cache misses is 100%. Notice that in S4 state, network control mechanism like the distribution PFC will work to avoid leak queuing. And in this case, CPU has opportunities to consume massive message before new data arrive. So the S4 states can transfer to S1, S2, or S3 states. From this figure, we can note that the system will fluctuate among the 4 states. And more time spent in S3 and S4 means higher I/O congestion. Narrow down the speed gap can slow down even avoid the state transfer. We choose 2 common scenarios of data center and increase the speed mismatch gap to validate our modeling. The scenario 1 is single flow with different application behavior. With tickets per packet increase, CPU processing rate decreases. And the scenario 2 is mixed flows with different network behavior. With large number of long flows increases, network ingress rate increases. We deploy eRPC, a popular high-performance RPC framework, on 2 servers with 200 Gbps C*7 leak to conduct this experiment. From the figure below, we can see that with the processing rate decreasing or ingress rate increasing, the cache misses line become higher and the end-to-end throughput performance degrades. Based on our modeling, we designed CARC, which is short for cache-aware rate control, to ensure speed match and avoid I/O congestion. The key idea is credit-based rate control. CARC maintains a credit pool for each RDMA connection, where each credit represents a cache line in receiver's LLC. When the sender sends an RDMA request, the CARC first checks the available credit and only posts the request to ALIC if the credits are enough. Otherwise, the request is blocked until credits are replenished. When the receiver finishes processing the data, it will trigger CARC to return the corresponding credit. By doing so, sending rates will match perfectly with receiver's rates, and our system will keep staying in the state 1 or state 2, where the cache misses rate is low. Besides, in order to tolerate the coordination error due to RTT latency and I/O unrelated memory access, we introduce loosened credit to adjust the credit dynamically. For instance, to cover the RTT delay of credit return, loosened credit equals to RTT divided by request processing time, which with such subscription, we can eliminate the receiver idle time, as this figure shows. In our evaluation, we use same setting with previous validation experiments, and the results show that CARC can reduce tail latency by up to 1.4 times, and improve throughput by up to 1.35 times compared to host CC. Thanks for your listening. Any questions are welcome.
Okay. Any questions? Any questions? Okay. So let me see the title. Is the rate control for the I/O resource competition, or?
Yeah.
So what's the interaction between the rate control for networking contention and the NIC resource contention? What's the relationships between these two contentions? I mean, how do you solve them?
The network congestion control use the signal from the switches or the RTT delay, and my rate control is focused on the host cache resource. So we need to use the resources like the cache occupies. And the control.
So final results is the minimum of the two rate control. I mean, for each flow, the minimum of two, right? You have two rate control mechanism, one for the NIC resources, one from the congestion control. So needed to take the minimum, or?
Yeah, actually, my rate control congestion can work with any network congestion control mechanism, and the final result is take the minimum of them. The sending rate is limited by either by my rate control or either by the network congestion control, and the final result is the minimum of them.
Okay. KK, yeah.
DDIO trying to handle the cache. How important is this problem when you have larger scale? This seems like you're trying to deal with synchronous flows when it's predominantly a small number of flows doing I/O, and you're trying to avoid the cache misses on the first and second level cache on.
Yes. This is a scalability problem, I guess. And in order to solve this problem, all mechanism do not use the basic credit that is limited by the IC size. We enable a Lucent credit, which enables the flows to have extra credit to DMA data, to send data. And this Lucent credit, I have a theoretical proof that to prove it will not overflow the IRC, because this is decided by the processing rate of a receiver, that if you have so many flows, but the processing rate is high, so you actually do not need many space to store your data. You can just use really small buffer size to accumulate your data, because receiver can process it very fast.
Okay. No more questions? Okay. Let's thanks the presenter again. Thank you.